trivial at all to reunite the empty branch, the one which we don't see in reality, and our actual result, and bring them together to the previous superposition state. So this picture is even harder to reverse in time. If we have now a quantum gas and some of its atoms collapse, this defines another error of time. The error of time just created by collapse. So we claim in this work that this error of time can be reversed as well when using a proper post selection, that is a proper boundary condition of the system and in general of the universe itself. So what I'm actually talking here about is initial and final conditions of the system.
Eliana,
yeah.
Is it simple to say rapidly how if you pick the right boundary condition, you can reverse, I guess, collapse?
Yes, so this is the main point. In classical thermodynamics, there is a final state. If we just reverse the velocities of all atoms, then they will return to the original state. This can be done. But to take a quantum system that has already collapsed and we see only the collapsed outcome, it is much harder to reverse this process. And some people talk about super technology that in the future would allow to reunite maybe parallel worlds. But if we think about Avogadro number of measured systems, Avogadro number of collapsed systems, this is currently impossible to reverse because we need to know the quantum state of 10 to the power of 26 particles. So this is much harder, and this error of time can be sort of can be imagined as a stricter one. There is also another error of time which is even harder to flip and might even be impossible to flip. The error of time we encounter in black holes, that is when we send a pure state to a quantum black hole, we get a mixed state, we get some thermal radiation, so information is lost, is believed, or some people claim that information is lost within black holes. But even in this case, time can be reversed, and there are some models on which we are working where post-selection can reverse the evolution, can reverse the information loss in black holes. So why am I beginning with this? The reason is the following. The reason is quantum collapse and the asymmetry it brings to quantum mechanics. So when we think about unitary processes, we think about some reversal dynamics. We know that a unitary transformation can be inverse, it has its inverse. So Schrödinger evolution in time, quantum mechanics is reversible. But all of this changes once collapse occurs. So when we have the non-unitary collapse, we have a genuine asymmetry in the system. And this was described as an ugly scar of what would have been a beautiful theory. So we see quantum mechanics is time symmetric until we meet collapse. And this is why people thought about the many worlds. This is, I guess, the main motivation for invoking the many worlds interpretation. Because in the many worlds interpretation, collapse never occurs. We have all the possibilities, one in our world, one in another world. So we have this many worlds picture where time reversibility is maintained, but we pay a huge price. We add into the description of reality infinitely many worlds, which we don't actually see. So I would try to claim that this picture of collapse can be also time reversed when one employs a special boundary condition on the system. So I will skip the mathematical technical details because I believe that not everyone here is familiar with this notation and the von Neumann measurement. But what I would like to bear in mind is just the quantum measurement process. That is, if we have a system we want to measure, we couple it to another system which has some quantum ingredient. And this quantum ingredient gets entangled with our system before being strongly measured. And a strong measurement of this measuring device would tell us what is the state of our system. So this is in general the von Neumann measurement scheme, and